Hello friends, a stunning new analysis of a data from NASA's Fermi Gamma Ray Space Telescope has revealed one of the most compelling pieces of the evidence yet for the dark matter. Join me as I dive into the data showing a consistent pattern of gamma rays emanating from the Milky Way's galactical center, a pattern that closely matches the theoretical signature of the dark matter annihilation. Let us explore this further. Hello everyone and welcome back. Today we are diving into one of the most profound mystery of our universe, a mystery that could be on the verge of being solved. Thanks to a small but mighty space telescope, we are talking about the dark matter. For decades, scientists have known this is something which is fundamental, is missing from our cosmic equations. The visible matter we see, which are stars, planets, galaxies, it's just not enough to explain how the universe works, how galaxy spins, or how cosmic structure formed. There is an invisible, undetectable stuff out there, far more abundant than anything we can see, and it holds the universe together. And this is called dark matter because we don't know what it is. And now, a potential breakthrough. New analysis of data from NASA's Fermi Gamma Ray Space Telescope suggests we might have finally spotted its elusive signature. This could be the moment we have been waiting for. So, what exactly is this dark matter? Imagine trying to figure out what's in a room, but you can only see the things that glow. You might notice the light bulb, the TV screen, but you would completely miss the wall, the furniture, maybe even other people. That's a bit like our view of the universe. We infer dark matter's existence not because we can see it, but because we see its gravitational effect. Galaxies spin much faster than they should if they only contain the stars and the gas we observe. Clusters of galaxies are heavier than they appear. When the light from the distant galaxies bend around the closer ones, it tells us there is far more mass than meets the eye. Scientists estimate that dark matter makes about 27% of the total mass energy of the universe, compared to only about 5% for the normal matter. That's make up, guys like you, me, and everything we can touch and see. The rest is dark energy. Another profound mystery for another time. But what is it made of? That's the $1 million question, maybe $1 billion question. We believe it's made of exotic particles that don't interact with light or other electromagnetic forces, which is why we can't see them. They barely interact with normal matter at all, except through gravity. They are truly dark. That means they don't emit any sort of signals for us to detect. Finding something that doesn't interact with anything else, as you can imagine, is incredibly difficult. Scientists have built massive underground detectors hoping to catch a rare ping from a dark matter particle colliding with a regular atom. Others look for cosmic rays or gravitational waves that might hint at its presence. But one of the most promising way to detect dark matter is to look for the tiny burst of energy released if two dark matter particles were to collide and destroy each other, a process called annihilation. Imagine two invisible billiard balls. You can't see them, but if they hit each other hard enough and turned into something visible like a puff of smoke or a tiny flash, then you would know they were there. For certain theoretical models of dark matter, specifically a class of particles called WIMPs, weakly interacting massive particles, this annihilation process is predicted to produce detectable high energy particles like gamma rays. This is where the NASA's Fermi Gamma Ray Space Telescopes comes in. Launched in 2008, Fermi is designed to detect the highest energy light in the universe, which is the gamma ray. These powerful rays are produced by one of the most extreme event in the cosmos, like supernova explosions, pulsars, supermassive black holes, devouring matter, and potentially dark matter annihilation. Fermi constantly scans the sky, creating map of gamma ray sources. Its primary instrument, the Large Area Telescope (LAT), is incredibly sensitive, allowing scientists to pinpoint the sources of these high energy photons and remarkably with lot of precision. One region that Fermi has paid particular attention to is very heart of our own galaxy, the Milky Way galactical center. Why? Because the theory predicts that if dark matter particles exist and are annihilating, this is exactly where we would expect to see the strongest signal. The center of the galaxy is thought to be the densest concentration of the dark matter in our region of space, like the giant cosmic beehive, where these particles could be mostly likely to bump into each other because they are clustered together. And for years, Fermi data has shown something intriguing around the galactical center, an axis of gamma rays. It's often called the galactical center gamma rays axis, or GCE. Scientists find abbreviation for everything. All right, moving on. Initially, scientists debated if the GCE was truly a dark matter signal or if it could be explained by a conventional astrophysical source. The galactical center is a chaotic place full of pulsars, black holes, and other phenomena that also produce gamma rays. It's like trying to hear a specific whispered conversation in a very noisy room. However, a new meticulously analyzed signal of over a decade of Fermi data has significantly strengthened the case for dark matter. Researchers have employed advanced techniques to separate potential dark matter signals from all the astrophysical noise. They have looked at the energy spectrum of these gamma rays, their distribution, and their consistency. What they found is remarkable. A persistent pattern of gamma ray emanating from a galactical center that across the multiple studies and different analytical approaches closely matches the theoretical signature of the dark matter annihilation. This pattern isn't just random flicker. It's a halo of gamma ray surrounding the galactical core with an energy distribution that aligns perfectly with what we would expect if the winds of a certain mass were annihilating. It's not coming from a bright distant point like pulsars. It is a diffuse smooth glow, precisely what a cloud of annihilating dark matter would produce. This is being hailed as a potential breakthrough because the consistency of this signal across various independent analyses makes it much harder to dismiss. It is not just a hunch, it's a robust statistical finding that aligns beautifully with our theoretical predictions of how dark matter would behave. If this truly is dark matter, it would not only confirm its existence but also gives us a vital clue about its properties, its mass, how strong it interacts, and how it is distributed in our galaxy. This would be a monumental step, fundamentally changing our understanding of the cosmos. However, and exciting as this is, scientists are still urging caution, and for a good reason. The scientific method demands rigorous proof. While the dark matter explanation fits very well, we cannot definitely rule out all other possibilities just yet. One prominent alternative explanation for the GCE is the population of undetected, rapidly spinning neutron stars called the millisecond pulsars. These pulsars also produce gamma rays, and if they are, many of them clumped together in the galactical center that are too dim or distant for Fermi to resolve individually, their combined glow could mimic a dark matter signal. Distinguishing between the two scenarios is incredibly challenging, but the latest analyses are being increasingly sophisticated, making the dark matter explanation even more compelling. It's like finding a needle in the haystack. And not now we think that we have a strong candidate. So what happens now? The search continues with even greater intensity. More Fermi data will be gathered. Other telescopes, like gamma ray observatories, both current and future, will attempt to confirm or refute Fermi's finding. There is going to be attempt to directly detect or probably come up with new experiments to have a direct interaction. Then also particle colliders. Experiments like the Large Hadron Colliders are also trying to create dark matter particles in controlled environment, which would be then ultimately confirmed. The journey to understand dark matter is long and challenging one, but these latest results from Fermi provide an incredible beacon of hope. We are getting closer to peeling back the veil of one of the universe's deepest secrets. The potential dark matter signature spotted by Fermi is a testament to human curiosity and our relentless pursuit of knowledge. It reminds us that our universe is far more complex and mysterious than we often imagine, filled with unseen forces shaping its destiny. Whether this signal ultimately proves to be an definitive evidence of the dark matter or lead us down a new avenue of research, one thing is certain. We are living in an era of unprecedented discovery, constantly pushing the boundaries of what we know. So friends, thank you for joining me on this incredible journey. Don't forget to like and share and subscribe for more insight into amazing world of science and space. See you next time.